Hello students, welcome to the lecture on database administration, and after the lecture we will be able to learn the following objectives. Define the concept of database administration. Discuss about the failure classification in database administration. Explain the storage hierarchy. Describe the RAID. Discuss about the transaction model. Explain the data dictionary storage. Let's start with a brief introduction to the database administration. Database administration is a job whose primary function is the overall support of a computer database. These support tasks are performed by a person called a database administrator or DBA. Databases require constant management and upkeep, and a DBA is specially trained to perform all of the necessary functions to do so. A DBA is normally required to have certification or a degree in supporting a specific type of database system such as Oracle or Microsoft SQL Server. Typically, he or she will use a database management system or a DBMS software package containing programs designed to aid in database administration. Using a database management system software package greatly enhances the ability of the DBA to effectively support the database. It allows the data in the database to be easily managed, organized, and retrieved. They can interact with different types of database models such as network or relational models. They provide a convenient means to query the data stored there, as well as an easy method for inserting, updating, and deleting records. Database management systems also help maintain data integrity and control access. Now we will talk about database administration. The term database administration states as how the databases are handled properly, how can manipulate, and how can be kept as secure. The person who cares for the entire database is called as database administrator. A database administrator, short form DBA, is a person responsible for the installation, configuration, upgrade, administration, monitoring, and maintenance of the physical databases. The DBA's responsibilities include the following: deciding the information content of the database, that is, identifying the entities of interest to the enterprise and the information to be recorded about those entities. This is defined by writing the conceptual schema using the DDL. Deciding the storage structure and the access strategy, that is how the data is to be represented, by writing the storage structure definition. The associated internal conceptual schema must also be specified using the DDL. Liaising with users, that is to ensure that the data they require is available, and to write the necessary external schemas and conceptual external mapping, again using DDL. Defining authorization checks and validation procedures. Authorization checks and validation procedures are extensions to the conceptual schema and can be specified using the DDL. Defining a strategy for backup and recovery. The types of DBAs. There are DBAs who focus on logical design and DBAs who focus on physical design. DBAs who specialize in building systems and DBAs who specialize in maintaining and tuning systems, especially DBAs and general purpose DBAs. Truly, the job of a DBA encompasses many roles. The role of a database administrator. A database administrator, DBA, directs or performs all activities that is related to maintaining a successful database environment. The responsibilities include designing database design and modeling, implementing and maintaining the database system, establishing policies and procedures pertaining to the management, security, maintenance, and use of the database management system, and training employees in database management and use.
Do you know what exactly a database administrator, also called DBA, does all day long? Protecting the data is number one job for a DBA. However, a DBA has many other jobs as well. Here are the tasks common to all DBAs. Installation. System administrators are responsible to look after an operating system on a given server. However, DBAs are responsible for installation of database software. A DBA is expected to possess knowledge of the hardware prerequisites from the perspective of database software installation, and to communicate the requirements to the system administrator. DBAs perform the installation as well as configure the database as per the requirements. Upgrades. New releases and patches are continuously developed. DBAs decide which patches are appropriate to install and also execute the upgrade process. Migration. If a server is being replaced with a new one, for one reason or the other, it is a DBA who will execute the transfer of data from old machine to the new one. Backup and recovery. It is a responsibility of DBAs to develop, implement, and periodically test a backup and recovery plan for the databases. Even in environments where a separate system administrator performs server backups, it is the DBA who is finally responsible for making sure that the backups are being done as scheduled and also that they include all the necessary data. Failures do occur. When a failure occurs, DBA needs to know how to use the backups to restore the database to operational state as soon as possible. Cost analysis. There is a cost to perform backups from a business perspective. It is a role of a DBA to make the management aware of the cost and risk trade-offs using various methods. Database security. A database is a repository of important pieces of information. This makes them an attractive target for hackers. A DBA must understand security model that the database software offers, and how to effectively implement the models. Storage and capacity planning. The primary purpose of a database is to store data. It is DBA's responsibility to plan the disk storage and to monitor available disk space. DBA must keep an eye on growth trends so that they can advise management on capacity planning. Performance monitoring and tuning. DBAs monitor database servers on an ongoing basis to identify bottlenecks and to provide solutions. Bottlenecks are simply parts of the system that are slowing down the processing. Database tuning could be done on multiple levels, for instance operating system, database configuration, applications etc. DBAs advise best solution. Assisting developers. DBAs should proactively take part in tuning the application being developed. It is easier to design performance into an application from the start, rather than waiting for problems to occur and fix them. DBAs work closely with developers of applications to make sure that best practices are followed. Troubleshooting. Problems do occur every now and then. DBAs are good at troubleshooting. They follow a logical approach to find out the root cause when things go wrong with database server.
The importance of DBA. The DBA has a very important role in the company, but it is often not defined completely. There is quite a difference in the DBA role for small companies to large enterprises. With the SQL Server availability at affordable price and growing information needs, many small companies are hiring database administrators in the company. Now let's discuss about the failure classification. Transaction failure, logical error. The transaction cannot continue with its normal execution because of such things as bad input, data not found, or resource limit exceeded. System error. The system has entered an undesirable state, for example deadlock, as a result of which a transaction cannot continue with its normal execution. The transaction, however, can be re-executed at a later time. System crash. There is a hardware malfunction or a bug in the database software or the operating system that causes the loss of the content of volatile storage and brings transaction processing to a halt. The content of a non-volatile storage remains intact and is not corrupted. Disk failure. A disk block loses its contents as a result of either a head crash or a failure during a data transfer. Copies of data on other disks or archival backups on tertiary media such as tapes are used to recover from the failure. Management discipline of database administration. Database administration is rarely approached as a management discipline. The term discipline implies a plan and implementation according to that plan. When database administration is treated as a management discipline, the treatment of data within the organization will improve. It is a difference between being reactive and proactive. In contrast, the proactive DBA implements practices and procedures to avoid problems before they occur. A proactive database administrator develops and implements a strategic blueprint for deploying databases within the organization. This plan should address all phases of the application development life cycle. A data specialist, usually the DBA, should be involved during each phase of the cycle. The DBA is also responsible for migrating the new database from the test environment to the production environment. While the application is operational, the DBA performs a host of duties including assuring availability, performance monitoring, tuning, backup and recovery, and authorization management. Additionally, the DBA is in charge of setting up an ad hoc query environment that includes evaluating and implementing query and reporting tools, establishing policies and procedures to ensure efficient and hoc queries, and monitoring and tuning ad hoc SQL. A good DBA is integral to the entire application development life cycle. The DBA is in demand for his knowledge of data and the way in which data is managed by modern applications. Storage hierarchy. A data stored in a hierarchical format. This time, the data is arranged logically in a top-down format. In a hierarchical database, data is grouped in records which are subdivided into a series of segments. Primary storage, the fastest media but volatile, cache and main memory. Secondary storage, next level in hierarchy, non-volatile, moderately fast access time, also called online storage, that is flash memory, magnetic disk. Tertiary storage, lowest level in hierarchy, non-volatile, slow access time, also called offline storage, example magnetic tape and optical storage. Magnetic disk, read-write head positioned very close to the platter surface, almost touching it, reads or writes magnetically encoded information. Surface of platter divided into circular tracks, over 16,000 tracks per platter on typical hard disk. Each track is divided into sectors. A sector is the smallest unit of data that can be read or written. Current generation disks are less susceptible to such disastrous failures, although individual sectors may get corrupted. Disk controller, interfaces between the computer system and the disk drive hardware. Optimization of disk block access. Block. A contiguous sequence of sectors from a single track data is transferred between disk and main memory in block sizes range from 512 bytes to several kilobytes. Smaller blocks. More transfer from disk, larger blocks. More space wasted due to partially filled blocks. Typically, block sizes today range from 4 to 16 kilobytes. Disk arm scheduling algorithms order pending accesses to tracks so that disk arm movement is minimized. Elevator algorithm move disk arm in one direction from outer to inner tracks or vice versa, processing next request in that direction till no more request in that direction, then reverse direction and repeat. Optimization of disk block access. File organization. Optimize block access time by organizing the blocks to correspond to how data will be accessed. Example, store related information on the same or nearby cylinders. Files may get fragmented over time. Example, if data is inserted to or deleted from the file or free blocks on disk are scattered and newly created file has its blocks scattered over the disk, sequential access to a fragmented file results in increased disk arm movement. Some systems have utilities to defragment the file system in order to speed up file access. Let us discuss about RAID. The RAID stands for Redundant Arrays of Independent Disk. RAID is the use of multiple disk and data distribution techniques to get better resilience and or performance. The RAID can be implemented in software or hardware or any combination of both. This presentation is a simple introduction to the RAID levels with some information on caching and different I/O profiles. Redundant arrays of independent disks. Disorganization techniques that manage a large number of disks, providing a view of a single disk of high capacity and high speed by using multiple disks in parallel, and high reliability by storing data redundantly so that data can be recovered even if a disk fails. The chance that some disk out of a set of n disks will fail is much higher than the chance that a specific single disk will fail. Improvement of reliability via redundancy. Redundancy store extra information that can be used to rebuild information lost in a disk failure. Example, mirroring or shadowing. Duplicate every disk. Logical disk consists of two physical disks. Improvement in performance via parallelism. Two main goals of parallelism in a disk system. Load balance multiple small accesses to increase throughput. Parallelize large accesses to reduce response time. RAIDs are redundant arrays of inexpensive disk. There are 6 levels of organizing these disks. 0. Non-redundant striping. 1. Mirrored disk and 2. Memory style error correcting codes. 3. Bit interleaved parity. 4. Block interleaved parity. 5. Blocked interleaved distributed parity. 6. P plus Q redundancy. The RAID level schemes to provide redundancy at lower cost by using disk striping combined with parity bits. Different RAID organizations or RAID levels have differing cost, performance and reliability characteristics. RAID level 1. Mirrored disk with block striping offers best write performance. popular for applications such as storing log files in a database system. RAID Level 2, Memory Style Error Correcting Codes (ECC) with bit striping. RAID Level 3, faster data transfer than with a single disk but fewer IOs per second since every disk has to participate in every IO. Subsumes Level 2 provides all its benefits at lower cost. RAID Level 4, block interleaved parity uses block level striping and keeps a parity block on a separate disk for corresponding blocks from n other disks. When writing data block, corresponding block of parity bits must also be computed and written to parity disk. RAID Level 5, block interleaved distributed parity, partitions data and parity among all n plus 1 disks rather than storing data in n disks and parity in one disk. Example, with 5 disk, parity block for nth set of blocks is stored on disk n mod 5 plus 1 with the data block stored on the other 4 disks. Higher IO rates than Level 4. RAID Level 6, P plus Q redundancy scheme similar to Level 5 but stores extra redundant information to guard against multiple disk failures. Better reliability than Level 5 at a higher cost, not used as widely. Hardware issues, software RAID. The RAID implementation is done entirely in software with no special hardware support. The RAID implementations with special hardware use non-volatile RAM to record writes that are being executed. Power failure during writes can result in corrupted disk. Example, failure after writing one block but before writing the second in a mirrored system. Such corrupted data must be detected when power is restored. Recovery from corruption is similar to recovery from the failed disk. NVRAM helps to efficiently detect potentially corrupted blocks. Otherwise, all blocks of disk must be read and compared with mirror parity block.
On most personal computers, there is a direct relationship between each user volume and a physical disk. For example, on a Windows PC, the C drive is usually a single physical hard disk or solid-state drive. On some computers, one single hard disk may be subdivided or partitioned into multiple volumes. Or alternatively, an extra hard disk may be fitted as another volume. However, in all of these instances, the data stored in each volume resides on a single drive. This makes for the easiest and cheapest hardware configuration. But it also means that if a drive fails, all of the data on its volume or volumes is likely to be lost. Data read and write speeds are also limited to the performance of a single disk. To protect against possible data loss and/or to improve performance, a technology called RAID stores the data in each volume on multiple physical drives. RAID stands for Redundant Array of Independent Disks and is widely used on servers and high-end workstations. Many PC motherboards now include a RAID controller that permits 2 or more drives to be linked together to operate as a single storage device. For some computing activities, such as editing high-quality, high-definition video, RAID is also pretty much essential. When setting up RAID storage, a number of options are available. The first is called RAID 0. This divides or strips the data in a storage volume across 2 or more disks, with half of each file written to one disk and half to another. This improves overall read-write performance without sacrificing capacity. So, for example, 2 1 TB drives may be linked to form a 2 TB array. Because this virtual volume is faster than either of its component disks, RAID 0 is commonly used on video editing workstations. In contrast to RAID 0, RAID 1 is primarily intended to protect data against hardware failure. Here, data is duplicated or mirrored across 2 or more disks. The data redundancy so created means that if one physical drive fails, there is still a complete copy of its contents on another drive. However, this does mean that drive capacity is sacrificed. For example, a 1 TB RAID 1 volume requires 2 1 TB disks. While data write performance is not improved by using RAID 1, data read times are increased as multiple files can be accessed simultaneously from different physical disks. If more than 2 drives are used, several other configurations become possible. For example, using 3 or more drives, RAID 5 strikes a balance between speed and redundancy by stripping data across 2 drives, but also writing parity data to a third. Parity data maintains a record of the differences between the blocks of data on the other drives, in turn permitting file restoration in the event of a drive failure. Finally, in common use, RAID 10 strips and mirrors data across 4 or more drives to provide the gold standard in performance and redundancy.
Transaction model. A transaction is a set of related and interdependent steps that form a logical unit of work. Grouping the steps into a transaction ensures that the set of steps are treated as an atomic unit. Either the entire set of steps succeeds or the entire set of steps fail. As a transaction is executing, it locks the part of the database that it is modifying, making the data unavailable for modifications by other transactions. Isolation of data from outside interference is one of the defining qualities of transactions. If the transaction's operations succeed, the transaction completes by writing changes to disk in a commit operation. A commit operation releases the transaction's locks, making the updated data available to other transactions. If an error occurs partway through execution, making it impossible for the entire transaction to succeed, the entire transaction fails. Rather than leave partial results in the database, the transaction backs out the changes that it has already made, leaving the database with the values that it has before the transaction started. The backout process is called rollback. The ACID model is one of the oldest and most important concepts of database theory. It sets forward 4 goals that every database management system must strive to achieve: atomicity, consistency, isolation, and durability. No database that fails to meet any of these 4 goals can be considered reliable. Atomicity. Atomicity states that database modifications must follow an all or nothing rule. Each transaction is said to be atomic. If one part of the transaction fails, the entire transaction fails. Consistency. Consistency states that only valid data will be written to the database. If for some reason a transaction is executed that violates the database's consistency rules, the entire transaction will be rolled back and the database will be restored to a state consistent with those rules. Isolation. Isolation requires that multiple transactions occurring at the same time not impact each other's execution. Durability. Durability ensures that any transaction committed to the database will not be lost. Durability is ensured through the use of database backups and transaction logs that facilitate the restoration of committed transactions in spite of any subsequent software or hardware failures. Now let's talk about data dictionary storages, DDS. The database also needs to store information about the relations known as the data dictionary. This includes the names of the relations, names of attributes of relations, domains and lengths of attributes, names and the definitions of views, integrity constraints, example key constraints, plus data on the system users, names of authorized users, accounting information about users, plus possibly the statistical and descriptive data, the number of tuples in each relationship, the method of storage used for each relation, example clustered or non-clustered. Where we will also see a need to store information about each index on each relation, the name of the index, the name of the relation being indexed, attributes the index is on, the type of index. The RDBMS needs to maintain data about the relation such as the schema. This is stored in a data dictionary, sometimes called a system catalog. Names of the relations, names of the attributes of each relation, domains and lengths of attributes, the names of views defined on the database, and the definitions of those views. Integrity constraints, names of authorized users, accounting information about the users, the number of tuples in each relation. The data dictionary consists of record types or tables that are created in the database by systems-generated command files tailored for each support backend DBMS. Command files contain SQL, statements for create table, create unique index, alter table for referential integrity using the specific statements required by that type of database. A tool for recording and processing information, metadata, about the data an organization uses. A central catalog for metadata can be integrated within DBMS or be separate, may be referenced during system design, programming, and by actively executing programs. It can be used as a repository for common code, example library routines. DDS benefits. The benefits of a DDS are mainly due to the fact that it is a central store of information about the database. Benefits include improved documentation and control, consistency in data use, easier data analysis, reduced data redundancy, simpler programming, the enforcement of standards, better means of estimating the effect of change. DDS facilities. A DDS should provide the set of facilities to record and analyze data requirements independently of how they are going to be met, conceptual data models, entities, attributes, relationships, to record and design decisions in terms of database or file structures implemented and the programs which access them internal schema. One of the main functions of a DDS is to show the relationship between the conceptual and implementation views. Let's now summarize what we have learned in this lecture. A database administrator, short form DBA, is a person responsible for the installation, configuration, upgrade, administration, monitoring, and the maintenance of physical databases. The DBA is usually expected to have experience with one or more of the major database management products, such as the structured query language, SAP, and Oracle-based database management software. The DBA is usually expected to have experience with one or more of the major database management products such as structured query language, SAP, and Oracle-based database management software. A disk block loses its contents as a result of either a head crash or failure during a data transfer. Copies of data on other disk or archival backups on tertiary media such as tapes are used to recover from the failure. There is a hardware malfunction or a bug in the database software or the operating system that causes the loss of the content of volatile storage and brings transaction processing to a halt. The content of the non-volatile storage remains intact and is not corrupted. The RAID level schemes to provide redundancy at lower cost by using disk striping combined with parity bits. Different RAID organizations or RAID levels have differing cost, performance, and reliability characteristics. RAID level 1.